All right, today we're going to take a look at colligative properties here in chapter 13, and a colligative property is a property of a substance that is affected by a concentration of solute in it. So when we're talking about colligative properties, we're talking about like a solvent that has something dissolved in it, its properties that change as a result of having solute particles mixed in with it. So like when I talk about colligative properties, I'm referring to properties of the solvent. So like water being my solvent, if I have particles mixed into it, these are the properties that will be affected by that. So our list of properties that are affected, vapor pressure lowering. So vapor pressure is going to be affected by the presence of solute particles. So water's vapor pressure should be lower with solute present. Boiling point elevation. So that means that with water as my solvent, its boiling point will be higher than usual, so higher than the usual 100 degrees Celsius. Melting point depression as a result of water having solute particles mixed into it, the melting point will be lower than it normally would be. And then lastly, we've got osmotic pressure, which really is something we deal with in biological systems and cells, but we'll mention that while we're on the topic. So again, I'm mentioning water as my example solvent. That's one we work with the most often. But we're talking about any solvent. These are the properties that are affected by the presence of solute. And so we're going to take a look at why that is and how you can calculate what the new boiling point, vapor pressure, melting point would be, etc. Okay, so let's first look at vapor pressure, because the vapor pressure and the boiling point are actually extremely tied together. We know from the definition of boiling point that it's the temperature at which the vapor pressure equals atmospheric pressure. So obviously, when we talk about vapor pressure being affected, it's going to affect boiling point as well. So you notice the picture here. We know that liquid evaporates a certain amount in a closed container. There'll be a certain number of particles. They exert a pressure. That's where vapor pressure comes from. The addition of these solute particles, these red particles that they have here, that's going to reduce the rate at which the vaporization occurs. So that means that fewer particles are going to be able to escape from the liquid than would if it was a pure substance. And if you think about that, we know that evaporation happens along the surface of the liquid, where the any particles that have a high enough kinetic energy to break free make their way into the gaseous phase, and then some reattach themselves if they come back in contact with the surface. That's this equilibrium system. And so notice though, what happens is that we do have some solute particles then that are sort of blocking the surface from, so there's not as many solvent particles, still a good number of them, but not as many solvent particles that are able to make it to the surface and escape. Another thing though, in addition to just blockage at the surface and not having a route to exit, the other thing though is, these non-volatile solute particles, meaning like if I have an ionic compound, it's not going to be volatile. It itself is not vaporizing. Those attractions with the solvent particles are keeping the solvent particles from being able to make their way out, meaning they might have some stronger, like that ion dipole attractive force that we talked about. That might be more difficult to overcome than just the intermolecular forces that we talked about in the last unit. So as a result of having these particles of solute mixed in, the vapor pressure is going to be lowered because it's more difficult for the liquid solvent particles to vaporize, and therefore the result is a lower overall vapor pressure. So the more particles we have, so the more of these red solute particles we'd see in here, the more of an effect we'd have, the more the vapor pressure would be lowered. So it's going to be related to the amount of solute particles that are present, how much the vapor pressure is lowered. So then if we look at, we have Raoult's law. And so if we ever talk about an ideal solution, that's something that follows Raoult's law exactly. If I wanted to figure out, well, how much is this vapor pressure of the solvent going to be affected, I can use this equation. So the new vapor pressure is going to be what's represented with PA. That equals that mole fraction. Notice this is mole fraction of compound A though. So when we're talking about vapor pressure depression, you're going to need to look at the mole fraction of the solvent. So usually, when we talk about concentrations, we're looking at the concentration of the solute. In this case, we want to have the mole fraction of solvent. So it's going to be, usually there's more solvent than solute. So it's going to be, pretty high number, of course, depending on how much solute you have in, but definitely higher than we're used to. when we're just looking at solutes. And then this is the regular vapor pressure. If that solvent was left alone, was pure, what would its vapor pressure be? So you're basically just taking the proportion of the moles of the solvent to total amount of moles of solution times the usual vapor pressure. All right, so here's a problem which you can find in your book, sample exercise 13.7. We have glycerin, non-volatile, non-electrolyte, so that means that those particles of solute are not going to be evaporating. There's a density of 1.26 grams per milliliter for that. We want to know the vapor pressure of water if we've added 50 milliliters of glycerin to 500 milliliters of water. And the normal vapor pressure of water at 25 degrees Celsius is 23.8 torr, and its density is 1.00 grams per milliliter. So the work is done for this problem in the book, and I'll also put up the slides. But we want to think about the strategy for this. So if we want to use Raoult's law, we have this, right? We have that pressure, vapor pressure of water normally is 23.8 torr. So we really need to solve for x, but this needs to be the mole fraction of water for the solution. So to get moles, well, that's why they're giving us densities. So we want to use this as the density of glycerin. So we have its volume. We can find the mass and then convert that to moles. Likewise, for the water, we've got the volume of water. We've got the density of water. Find the mass of water, and then find moles using molar mass. So then we've got moles of water. We can add together the two mole amounts, and then we're just multiplying the mole fraction. So that's what this says here. Again, you can pause this video and, or you can actually just look at this solution. It appears in your book. That's where I got it from. But there it is. So if you stopped and did the calculation, this is what you'd come up with. So take a minute to work through it and make sure you can see where everything comes from. But we will have worked through a mole fraction problem in class, and it's the same idea, but just make sure that you're using, since this needs to be the mole fraction of the solvent, it's a little bit different perspective than we're used to thinking of mole fractions usually for solute that we talk about. All right, so how does this tie in with the boiling point? Well, we know that we saw these vapor pressure curves, this arm of the phase diagram before, where if I am lowering the vapor pressure, so at a given temperature with the solute present, I'm lowering the vapor pressure. So that's what this second curve with the blue line is showing. And so if I'm at a lower vapor pressure, that's going to correspond to, well, again, we have to have vapor pressure equal to atmospheric pressure. So if I want to have a vapor pressure that's high enough, so let's say here's 1 atmosphere, I want to have a vapor pressure that's high enough to be equal to atmospheric pressure. Notice that instead of me reading along this line, like at this temperature, I've got a certain vapor pressure and it's equal to 1. With this lowered vapor pressure for the solution, then I'm going to have to get to that much higher of a temperature to end up with a vapor pressure that's equal to atmospheric pressure. So that's where the boiling point elevation really comes from. So it's, because of the same reason that the vapor pressure is lowered, that the boiling point ends up doing the opposite, that it's increased. And then we can also see from this curve, since this is a phase diagram, we see the same thing happening with freezing point, and we'll take a look at that one next. Notice this amount of increase, we're labeling that as delta TB. The amount of decrease for freezing point we'll label as delta TF, and so B being for boiling and F being for freezing. So delta means, well, this isn't the actual temperature, this is just the increase in temperature. So if we're using any of the calculations in the future to find the boiling point, the new boiling point, we first calculate the elevation, and then we calculate by adding that onto the old boiling point of the pure solvent, and likewise with the freezing point, we'll figure out that delta TB, and that's subtracted off of, or that's what's less than the regular melting point or freezing point of the pure substance. Okay, so here's the equation that I was referring to if you want to find delta TB. So there's a constant that is specific to each solvent. So this is a boiling point constant for each particular solvent. So that's just a value you look up. It's experimentally determined. And then notice that this is molality. So this is where we would use molality in these calculations. And again, in your lab, you're going to be mixing in, you'll have the molality calculated for your solutions, and you'll be mixing that in with the ice to see how much your temperature decreases below 0 degrees Celsius. But anyway, this is the equation you use. So obviously the higher the concentration, as we saw from looking at that Raoult's law equation, the higher the mole fraction of, the lower the mole fraction of solvent, that means the more the vapor pressure is going to be decreased. That would then mean the more concentrated the solution would be, and therefore the higher the boiling point is going to go. It's just a matter of plugging into the equation. And freezing point, same thing. So we've got constants for freezing point. Here's the equation for that. So it's the same exact equation, except we're using a constant specific to the solvent, and the molality is then, of course, of the the solute, the moles of solute per kilograms of solvent. And so there you go. Now, it doesn't matter what the identity of the particles are that we have dissolved. So, if I have a certain molality of sugar molecules dissolved in water versus the same molality of ammonia molecules dissolved in water, we're going to end up with, this equation. This is dependent, the constant Kb and Kf, those are dependent on the solvent. Molality, though, is just the concentration, the amount of particles. But what we have to take a look at is electrolytes. So we know that, when I talk about sugar dissolving, or when I talk about ammonia dissolving or some other molecular substance, those are not going to be producing any more than a 1-to-1 ratio of, for every 1 formula unit, for every 1 mole, I have 1 mole of solute particles released in solution. But that's not the case for electrolytes. For ionic compounds, we know that they dissociate, they break apart. And so we do have to factor in that, for every 1 formula unit of sodium chloride, I actually have 2 particles released into solution. I've got these, there's separate chloride ions and there's separate sodium ions. And so we would expect an electrolyte, because even at the same concentration, every single one of these breaks apart as well. And so that leads to an additional change in the properties of boiling point, freezing point. But it's not exactly going to be doubled. So we're going to look at how we could figure out, and it's called the Van Hoff factor. And so in changing the equation that I originally gave you, we're just looking at, well, how much, would it actually be twice the amount of particles for sodium chloride? And it's not quite as much. So notice what this is saying is that there's actually, as it turns out experimentally, even though we know the electrolytes are dissociated, they do some sticking together to some degree, and so we call that reassociation. And so it might not be quite twice the amount of solute particles for sodium chloride as a non-electrolyte. So here's some examples of, basically, the more dilute, the more likely the Van Hoff factor is close to the number of particles in your formula unit. So for example, sodium chloride, there's Na and Cl, so those would dissociate. And notice that these values get closer and closer to 2, so meaning there's 2 particles per formula unit, the lower this concentration gets. But again, we can still kind of use that estimate that at least gets us slightly in the ballpark of, like this potassium sulfate has 2 potassiums and 1 sulfate to dissociate when dissolved. And even though it's not quite 3, a Van Hoff factor of 3 particles per formula unit, again, as a dilute solution, it starts to get closer and closer to that. So this is how we'd modify the equation. So the Van Hoff factor, again, you can kind of make an estimate of equal to the number of electrolyte particles that would dissociate. And again, if we have a molecular compound covalently bonded, that Van Hoff factor will be just 1. But this is the modification to the original equation, because again, if I have the molality of just the sodium chloride solution, that doesn't take into account the fact that there's extra particles that dissociate for every 1 formula unit. All right, lastly, let's take a look at osmosis. And osmosis has to do with movement of fluids, or movement of particles through semi-permeable membranes. So they block smaller particles, they block larger particles and allow smaller particles to pass through. And this is, of course, something very, very important in biology, because that's how things get in and out of cells and how cells get the things that they need. So in osmosis, we are looking at the net movement of solvent from a higher solvent concentration. So that means if I have a low solute concentration, the solvent is going to move to the area of higher solute concentration or lower solvent concentration. So just like we've seen in other scenarios with like energy or heat moving from high concentration to low concentration, kind of the same idea where again, where there's more solvent and lesser solute, the solvent is going to flow towards the side that doesn't have as much solvent per solute. So that's what's depicted here in this picture. So we've got the pure solvent, we've got the solution with solute particles. So these particles are going to move through, the solvent particles are going to move through and basically lower the concentration over here. And again, as a result of the increase in solvent particles over here, then we end up with, I guess that's in this picture, we end up with an increase in pressure over here. So the pressure required to stop osmosis, so that's what this, what this little arm was showing, is this pressure being applied to stop osmosis. The symbol for that is this pi symbol, N divided by V, so moles divided by volume, which is molarity of the solution, times RT, so the molarity times RT is the calculation you can use to figure out the pressure required to stop osmosis, and therefore is the osmotic pressure. So the concentrations are the same on both sides, so if the osmotic pressure is the same on both sides of the equation, we call the solutions isotonic. So that, see that iso prefix again, referring to something being the same. So the concentration is the same, the pressure is the same. All right, so if this happens in the body, and if we're looking at what happens with blood cells, so if we have a high solute concentration outside the blood cell and a low solute concentration inside, there's the bell, we see the solvent, or liquid moving out of the cell, and so that results in a a loss of fluid from the cell, and so we call that crenation. And again, you can learn more about this in bio, just mentioning how this relates to what we're talking about here. And again, if the inside has a high solute concentration, the outside with a lower solute concentration, that means then that the solvent is going to travel inside, and then that's going to kind of blow up, and we call that hypotonic. And that would be hemolysis of the cell. Hopefully I'm pronouncing that correctly because I'm not a bio person. But anyway, we're mostly concerned with the vapor pressure, boiling point, and freezing point effects of having solute particles present, and we will be doing some calculations with that in the lab, the solution making lab that you did.